This video is about an integration technique called partial fraction decomposition. It's a pretty interesting technique. You use it when you see integral problems that look like big fractions. We got some equation on top divided by some equation on the bottom. So you would think that partial fraction decomposition is the quotient rule of differentiation in reverse, because if someone asked me to derive this guy, I would definitely use quotient rule. I have an equation on the top and I have an equation on the bottom. But actually, this technique, PFD, is not the inverse of quotient rule. It's its own thing, and it's kind of interesting. So let's get into it. So let's say we had to add these two fractions together. Well, we all know how to do that. You would do 8 times the numerator and denominator of this guy, and 5 times the numerator and denominator of this fraction to get that common denominator of 40. With that common denominator of 40, you could then directly add both, yielding an answer of 31 over 40. So this guy right here is kind of like these partial fraction decomposition types of integral problems. We're being asked to integrate some big disgusting looking fraction, and what PFD allows us to do is it allows us to take this fraction and go sort of back in time and split it into the components that made up that fraction in the first place. So we'll take this guy, do some steps that we'll go through and learn, and we'll end up with these two guys. And now integrating these two guys is a lot easier because I'll be able to integrate them, I'll be able to divide and conquer. Because that's what integration allows us to do. It allows us to split up the integral when there's adding or subtracting. So let's learn how to do that. So our first step is to take our problem and split the denominator into factors of either linear equations or quadratic equations. All that means is we want something that looks like this. See, this denominator is basically made up of a whole bunch of linear equations getting multiplied by each other. This one right here is one linear equation, that's x, and two quadratic equations, x squared plus 1. And there's two of them because of that squared. Here we got two linear equations getting multiplied by each other, and here we just have one linear equation. So for all these blue guys here, we don't need to do anything. We've already split that denominator. But for this guy right here, he would need to be split up into factors, into equations getting multiplied by each other. And that's just an algebra step, so I'll trust that you're pretty sharp on that scale. So this guy would be split up into 2x plus 1 times x plus 1. Alright, now we got it. Now the denominator has been split up into a bunch of equations getting multiplied by each other. And they can either be linear or quadratic equations. So these are two linear equations getting multiplied by each other. So this is all step 1 of PFD. So the next step is that each linear equation gets one constant over it, and each quadratic equation gets two constants over it. So my top one would just equal a over x minus 1. This one right here would equal a over 2x plus 1. So this linear equation gets one constant. And we have another linear equation here, so it gets its own constant as well. So I'm splitting the fraction based on its linear and quadratic equations, and each linear equation gets one constant, and each quadratic equation gets two constants. So if we skip down to that bottom one just to see that quadratic equation in action, my linear equation x would get one constant. Now here's the thing. We have a quadratic equation here, but notice what happens. But notice that this quadratic equation is repeated. Special things happen when you have linear or quadratic equations getting repeated. So I give the first rendition of that quadratic equation two constants, there we go, bx plus c. But since this equation is repeated, you have to give the second sort of rendition of it two constants as well. So this would be dx plus e. And let's go to our second to last equation here, and let's show how this repeated thing happens with linear equations. Let's say this y minus 3 was not by itself. Let's say there were 3 of them. Okay, so each linear equation gets one letter. So a over y, that's the first linear equation. The second linear equation is y plus 2, so it's a linear equation, so it gets its own letter. Now, our third linear equation is repeated 3 times. So it's going to be c over y minus 3, that's the first one, to the 1, plus d over y minus 3 squared for the second one, plus e over y minus 3 to the third, cubed. And for this one, this is an easy one. Just 2 linear equations. Each one of them is by itself. There are none that are repeated. So my first one gets a letter. Simple as that. My second one gets a letter. So this is step 2 right here. So this is our step 2. We're splitting up the fraction, the big, ugly fraction. Each linear equation of the denominator gets one constant, and each quadratic equation gets 2 constants. So a way you can remember this is, look at this linear equation, or think of any linear equation. What is the derivative of a linear equation? Well, just a number. In this case, it would be 2, based on that slope of that linear equation. So the derivative of a linear equation is just one number, a constant. That's why each linear equation gets just a number. Same for quadratic equations. The derivative of this guy here would be 2x. So the derivative of a quadratic equation is a linear equation. That's why each quadratic equation gets 2 constants. And of course, you want to be careful for this last part of step 2. If any equation is repeated, each version of the equation gets its own constants. So this can get pretty confusing, but this quadratic equation here, x squared plus 1, gets repeated twice. So the first version, as I like to call it, gets its own 2 constants, its own linear equation, as does the second version. And of course, this whole repetition thing goes for linear equations too. This guy is repeated 3 times, so the first version gets a constant, the second version gets his own constant, as does the third version. And so on and so forth. Be aware of that. So that is our step 2 right there. So for step 3, I'm going to choose to focus on this guy right here so I can show you step 3. So step 3 begins with multiplying both sides of our equation by the denominator here. So on the left side, we'll get a complete cancellation right here if I take our entire denominator and multiply it by the left side of the equation. We're just going to result with 2. And on the right side, this whole denominator comes in, boils with this first term, and we get 1 cancellation, and we're left with b times 2x plus 1. And it foils into the second term, and we get a cancellation with the 2x plus 1 and this 2x plus 1. So we're left with a times x plus 1. So now I have to figure out what a and b are. If you think about it, we've actually already split up our problem. Our big, disgusting fraction is just not completed yet. We've really got to figure out what are the values of these constants so we can complete this splitting up process. So if I wanted to figure out what b is, what I would do is I would plug in a value of x, a specific targeted value of x that would eliminate a and just leave b okay. So in this case, that value would be -1. So I would plug in -1 for x, -1 plus 1 is a 0. 0 times a is a big 0. And if I plug my -1 in here and do my math, what I'll end up with is 2 is equal to b times -1, and therefore b is equal to -2. Alright, so now we've got to find a somehow. So what specific value of x could I plug in that could eliminate the b? That would, in a sense, make this binomial here equal to 0, so 0 times b is a 0. Well, if I really think about that, that will be -1/2. Because -1/2 times 2 is -1. -1 plus 1 is 0. So that'll do it right there. So what I'm left with is 2 is equal to a x plus 1, and for x I plug in that -1/2. So -1/2 plus 1 is a +1/2, plus, and we know that this whole thing is one big 0. So if I solve for a is equal to 4. So that is our step 3 right there. So first we multiplied both sides of the equation by the denominator of our original fraction. So here is our equation, denominator of our original fraction, and we multiplied both sides of the equation by it. And we got some cancellations, did the algebra, ended up with this equation right here. And then we plugged in specific values of x that would allow you to solve for each constant. This is where you kind of have to look at the equation and see what the right thing is to do. You can plug in any value of x that you want, but we noticed that if we wanted to solve for b, we had to eliminate a. And how do we eliminate a? By plugging in -1 into this guy, and vice versa for a. If we wanted to solve for a, we had to eliminate b, which means we had to plug in the correct value for that was plug in -1/2. And that's what we did here. And that enabled us to find b and a. So that's step 3. Now the example that we just did was a pretty standard, pretty basic step 3. There are partial fraction decomposition problems out there where it's not as easy as this. Like for some situations you get to here, no matter what, you can't find a value of x that will get you one of the constants by itself. And we'll take a look at those more tough step 3 type problems in another video. Alright, so now that we know a and b now, we can write them in here. We've successfully taken in our initial big ugly fraction and split it up into much smaller pieces. And of course, don't forget that the original problem was to take the antiderivative, the integral of this whole thing. So same problem here, same equation, we've just split it up into much nicer pieces. And because we can split up integrals of equations that are sort of separated by addition and subtraction, our new integral here can be, and each one of these is a u sub step. So if you do the u sub, your final answer will be this. So that's how you do partial fraction decomposition. Got to split that denominator up into linear or quadratic equations, factors. Each linear one gets one constant, while each quadratic equation gets a linear equation, gets two constants in a sense, like ax plus b or cx plus d. And once you've done that split, you've got to rearrange it and you've got to figure out what each one of those constants are. And once that split is complete, that integral is a lot easier here. Now there's just one more thing you have to be aware of. We have this idea of improper fractions. What if the numerator is bigger than the denominator? And you know, when you see something like this, something you can do is you can make it proper again. 15 goes into 19 once with the remainder of 4. So 19 over 15 is equal to 1 and 4/15. So in a sense, 1 plus 4 over 15. Well, we have the same idea going on here, too. You may be faced with a partial fraction decomposition type of problem in which the numerator is bigger than the denominator. Well, how do I know that the numerator here is bigger than the denominator? Well, you can tell because the highest power of the numerator is bigger than the highest power of the denominator. So, if you run into a problem like this, you have to do long division. You basically have to do this right here. You have to properize that improper fraction. So you have to know polynomial long division here. And I have a video if you want an intro on polynomial long division, so check that out if you need a refresher. So we want to do our numerator divided by our denominator, just like we did 19 divided by 15. But we're dividing equations here, so I got to tap into that polynomial long division technique that I know. So what number do we multiply by this to eliminate our x cubed? The number would be just x. X goes into the x squared, makes an x cubed. Goes into the x, makes a negative x squared, and goes into the negative 6, and makes a negative 6x. And remember, we're taking this whole quantity and subtracting it. So the x cubes cancel. In a sense here we have a 0 times x squared term. So a 0 times x squared minus a negative x squared. We'll get a positive x squared. Negative 4x minus a negative 6x will make a positive 2x. And negative 10 minus, well, basically a 0 here, we'll just get negative 10. Alright, now we have to do this process again. What number should I multiply by this whole thing to cancel out my x squared? Well, a positive 1 will do it. Positive 1 into x squared gets us that x squared. Take that positive 1, multiply it into the negative x, gets a negative x. And positive 1 times negative 6 is a negative 6. And of course, we are subtracting this whole quantity. X squareds cancel, just like we designed it to. 2x minus a negative x is a 3x. And negative 10 minus negative 6 is a negative 4. So this thing is our remainder. So the answer to this division question here will be x plus 1. In a sense, that is the whole amount of times that it can go into the numerator, and plus the remainder divided by the divisor, the thing we were dividing into. So for us, that's going to be plus a remainder, 3x minus 4, over the divisor, the thing that we were using to do the division. And there we go. This whole thing is equal to this whole thing. And of course we want to take the integral of this. These guys are easy to derive. And to derive this piece, we would use our regular old step 1, step 2, step 3 partial fraction decomposition. So this right here is the absolute very first thing we have to do. Before doing any of the other steps we talked about, we always have to check the highest power of our numerator and the highest power of our denominator. If the highest power of our numerator, that's this guy, is greater than or equal to the highest power of the denominator, this guy, we have to do this whole long division step here. So keep in mind, if this guy was a 2 instead of a 3, we would still have to do that long division step. Be aware of that. If the highest power of the numerator is greater than or equal to the highest power of the denominator. Alright, well that Does it for the partial fraction decomposition technique. Steps 0 through 3, that is it right here. And if you want to see any practice examples worked out using these steps that we've developed, check the practice video.